Welcome back to Educator. We're in the Calculus 1 sequence and we're looking at computing volumes by means of the method of disks and washers. We looked at 3 specific examples in the main tutorial. Here I have 2 more generic examples to sort of rederive some familiar volume formulas from calculus, and it's pretty interesting how calculus lets us do this. So in this first problem, we're looking at y equals radical r squared minus x squared. If you're not sure what the graph of that would look like, you can square both sides, and we get y squared equals r squared minus x squared. So x squared plus y squared equals r squared. It's a circle of radius r centered at the origin. And so it is this circle here, and I'm only going to draw the first quadrant piece because we're on x equals 0 to x equals r, and we took the positive square root, so we're only looking at non-negative y values. So we're looking at this piece here in the first quadrant. It's being rotated about the x-axis, and the volume that we're building up is simply the volume of half of a sphere. The volume we're computing is half of a sphere of radius r. Now at this point, we could finish the problem without using calculus, but that's because we know the formula for the volume of a sphere. But that formula came from somewhere, and the integral we're about to do is one way to derive that formula, one way to create that formula from scratch. So this is going to be a problem by the method of disks. These disks are lined up horizontally, and we're rotating about the x-axis. The thickness of each disk is in the x direction, and that's how I remember that we'll be integrating with respect to x. I think the thickness is in the x direction. It's a dx sort of thing. We're integrating with respect to x. The cross sections are circles, and so we have a pi times radius squared. The radius is the distance from the curve to the x-axis, and that is radical r squared minus x squared minus 0. And the radius is being squared. And we're integrating from x equals 0 to out here where x equals r. Okay, now something really nice happens with this integral. There's a factor of pi that we can pull out, and we're squaring the radical, so the square root goes away. And we get a simple looking integrand of r squared minus x squared, and we integrate with respect to x. And so r is a constant, so r squared is still a constant, and so it integrates to r squared x. Just like 9, which is 3 squared, would integrate to 9x. R squared integrates to r squared x. And then x squared integrates to x cubed over 3. And we're on 0 to r. And we get pi times r squared times r minus r cubed over 3 minus pi times 0 minus 0. And we get r cubed minus a third r cubed, all times pi. That gives us a 2/3 pi r cubed. Now this was visually the area of half of a sphere, and from geometry classes you know that the volume of a full sphere of radius r is 4/3 pi r cubed, and our area of a half sphere, or excuse me, our volume of a half sphere did come out to 2/3 pi r cubed, which is half of 4/3 pi r cubed. And so we've confirmed or derived the formula for the volume of a sphere.